So in the last lecture, we were doing one example. So we are talking about the second order. Okay, second order ordinary differential equations. Okay, so as an example, y is equal to 1 plus sine of x and y is equal to 1 plus sine of x. And the differential equation is y double prime is equal to y double prime plus 1 y double prime plus y is equal to 1. So first we can verify this equation. Okay, so from this first solution, y is equal to 1 plus cosine x, which will be y prime is equal to minus sine x, and y double prime is equal to minus cosine x. So if I input these values over here, so it will be minus cosine x plus y. Plus y is 1 plus cosine x. 1 plus cosine x is equal to 1. That is the right hand side. So minus cosine x plus cosine x cancel, so it will be 1 is equal to 1. So it means that y is equal to 1 plus cosine x is the solution of y double prime plus y is equal to 1. Similarly, for the second, we can verify. So it will be y prime is equal to sine of x, y double prime will be equal to minus sine of x, and then inputting these values, y double prime is minus sine of x plus y, which is 1 plus sine of x. 1 plus sine of x is equal to 1. So minus sine of x plus sine of x, 1 is equal to 1. So this means that both are the solutions of this differential equation. However, can we now apply the principle of superposition for this differential equation? Remember that this is a non-homogeneous differential equation. So from the superposition, we assume that these two solutions can be combined by a linear combination. So we take C1 1 plus cosine x, and then plus C2 into 1 plus sine x. So y prime will be equal to C1 into minus sine x, and because it will be 0, 1 is 0, so plus C2 into cosine x. So y double prime will be equal to minus C1 cosine x, and then it will be minus C2 sine x. Okay, so now I input these values. So the differential equation was y double prime plus y is equal to 1. Yeah. So I input the value of y double prime, so minus minus C1 cosine of x minus C2 sine of x. Okay, so that is y prime, and then y is, yes, this one. So y is C1 plus C1 cosine of x plus C2 plus C2 sine of x is equal to 1 from here. So from here, minus C1 cosine of x plus C1 cosine of x, yeah, these two cancel. Minus C2 sine of x plus C2 sine of x cancels. But what we left is C1 plus C2 is equal to 1. So now here we cannot say that this left hand side and right hand sides are equal. So C1, C2 can be any values. So this means that the principle of superposition is not applicable here. So it means that the principle of superposition we cannot apply for a linear non-homogeneous equation. So in the previous example we did it in the lecture. We also said that the principle of superposition can also not be applied for the non-linear equation. So if the equation is either non-linear or linear horizontal, linear non-homogeneous, we cannot apply the principle of superposition. So principle of superposition is only applicable for the linear homogeneous equations. Okay. Now I will illustrate another aspect, which is the independence of solutions. Independence of solutions. So what does it mean? What do we mean by the independence of solutions? So in simple words, if we have, for example, two solutions. So let me show you. One example. If one solution is e power x, the other solution is e power minus x, and the differential equation is y double prime minus y is equal to 0. So we can verify that these are the solutions of this differential equation. So one by one we can verify. So y1, so it will be y1 prime will be e power x, y1 double prime will be e power x. Yes. So in this case, if we put it over here, so e power x minus e power x is equal to 0. 0 is equal to 0. The second solution is y2 prime minus e power minus x, and y2 double prime is it is e power minus x. So it will be e power minus x minus e power minus x. 0 is equal to 0. So since here we can see that these two solutions are the solutions of this differential equation, and then this differential equation is homogeneous and linear. So their from the principle of superposition, their linear combination c1 e power x plus c2 e power minus x will also be the solution of this differential equation. So this we can also verify. So y prime, it will be c1 e power x minus c2 e power minus x, and y double prime will be c1 e power x plus c2 e power minus x. So we can see that y prime minus y, so it is 0. Obviously it is 0, so it is y double prime, so c prime. So we can put it like this. So we can obviously see that y double prime minus y, so c1 e power x, c1 e power x, and c2 e power minus x, c2 e power minus x. So if we subtract y prime from y, so it will be 0. So this means that the principle of superposition holds, as we have stated before. But one thing we can see over here is that here if we take the ratio of these two individual solutions, y1 over y2, so it is e power x over e power minus x. So this ratio is e power 2x. So now e power 2x is not a constant value. Okay, it is in terms of x. It is not a constant value. So here we can make one conclusion that if we find two such solutions whose linear combination is also the solution of this homogeneous linear equation, then those two solutions are independent solutions. Okay, so you can call these two solutions as the independent solutions. So y1 is equal to e power x and y2 is equal to e power minus x are independent solutions. So for the independent solutions, principle of superposition holds. Okay, but let's see. So from now we can use this observation. That means our observation is that the two solutions for a second order differential equation, linear differential equations, are not constant. That means they can be related by a function. Okay, so it means that if we know one function y, and suppose that the second function is y2. So for example, if we know one solution which is y1 and the second solution we want to find, so then we know that this second solution y2 will be some multiple of y1 by some function. Okay, it will not be a constant, so u can be a function. So it means that we can make some substitution into the original differential equation like this, if we know one function, and then we can find the other function. So this gives rise to a method which is called as the reduction of order method. So which is a useful method, but this method requires knowledge of one solution from the differential equation. So reduction of order method. So this reduction of order method will use this type of substitution to reduce the order of the second order differential equation into the first order differential equation. And we know the method to solve the first order differential equation, and then we can find the solution, the second solution. So let's take the example. Okay, suppose that the differential equation is x square minus x times y double prime minus x y prime plus y is equal to 0. So suppose that we know one solution, which is y1 is equal to x. So we can verify that this solution, because in this case y1 prime will be 1 and y double prime will be 0. So x square minus x into y double prime, that is 0, minus x, y prime is 1, and then this is y is equal to 0. So this term is 0, this is minus x, and then this term is y is actually x. So 0 is equal to 0. So we verify that this is the solution of this equation. So we know one solution, but we want to find the second solution, y2. So second solution will be obviously be linearly independent, which means that it will be some function times the first solution. Okay, so y2 will be equal to u y1, or if we put the value of y1 over here, so we can put u x. Okay, so in this case just we represent y2 by y, so y is equal to ux. So this will become a kind of substitution into this equation. Okay, we can apply this substitution into this equation, and then we can I can show you that we can further simplify the second order equation into the first order equation. So that some substitution will be y prime will be equal to u x prime, which will be 1, plus x u prime. Okay, and then y double prime will be equal to u prime plus x u double prime plus u prime. So it will be 2u prime plus xu